Good day everyone. Today we're diving into hypothesis testing. Now, hypothesis testing is a key method in statistical analysis, particularly in the behavioral sciences where it's impractical to take a measure in the whole population. Hypothesis testing allows researchers to make informed inferences about a population by examining data from a sample. Since studying an entire population is usually impractical, we use this process to test specific claims, and it has four main steps. One is stating the hypothesis, setting decision criteria, computing a test statistic, and making a decision. These simple steps, not simple, but these steps helps us determine whether our results reflect real effects or if they're simply due to random chance. Now, let's dive in to step 1, state the hypothesis. The first step is to state our hypothesis, where we begin with the null hypothesis. We denote as HO, like H. This is the assumption that there's no effect or no difference or no relationship present in the population. It's essentially the status quo. So for example, we might say all dogs have 4 legs. This implies that there's no difference among dogs in terms of leg count. However, an alternative hypothesis, which is denoted as H1, would propose that there is indeed an effect or a difference or a relationship. So for example, 20% of dogs have only 3 legs. So this statement contradicts the null and suggests that not all dogs have 4 legs. So these hypotheses set the foundation for the statistical test that we will perform. Let's apply step 1 in a real-world example. So here, our dependent variable is the amount of alcohol consumed the night before a statistics exam. Then our independent variable or the treatment is whether students received a pamphlet discouraging drinking or they didn't receive one. So the null hypothesis would state that there is no difference in alcohol consumption between students who received the pamphlet or those who didn't. On the other hand, the alternative hypothesis suggests that there is a difference, perhaps that the pamphlet had an effect causing the treatment group to consume more or less alcohol than the control group. Step 2, set criteria for decision. So once we've stated our hypothesis, the next step is to set criteria for making a decision. So this involves choosing a level of significance, usually denoted by alpha or A. My common choice is 0.05, so we are taught that we will usually use that number, which means that we accept a 5% chance of making a type 1 error. Type 1 errors and type 2 errors will be further discussed in the following slides. So rejecting a true null, back to the topic where if we accept a 5% chance of making a type 1 error, we are rejecting a true null hypothesis. If the p-value we calculate from our test is less than alpha, or 0.05, we reject the null hypothesis. Also, we need to decide between a one-tailed test and two-tailed test, depending on the nature of our hypothesis. So, a two-tailed test is used when we're looking for any difference. So regardless of direction, it splits alpha between both ends of the distribution. And a one-tailed test is used when we're testing for an effect in one specific direction, such as placing all of the alpha in one tail. This decision influences how we interpret the statistical results. We'll walk through an example. Example, suppose an exam 1 from the previous semester had an average score of 85. We'll call that our population mean. Now we want to test whether a new treatment, maybe a new treatment or a teaching method, has an effect on exam scores. So we set up 2 hypotheses. The null hypothesis, where it assumes there's no effect, meaning the treatment group will also have a mean score of 85. The alternative hypothesis assumes there is a difference. The treatment group's mean score will be different from 85. So the graph here shows that the distribution of all possible means, assuming the null hypothesis is true. Most sample means will fall near the center, close to 85. These are high probability outcomes under null. However, values that fall far from the left to the right are extreme values and are considered low probability outcomes if the null is true. If our actual sample mean falls into one of these regions, we'll have grounds to reject the null hypothesis and support the alternative hypothesis. So in this step, we're defining where that cutoff is. So how extreme a result needs to be before we say it's unlikely to have happened just by chance.
Hi, good day everyone. So before I start, I would like to introduce myself. My name is Charls Labial. So as continue from what Jetrice reported, so I'm going to discuss about the hypothesis testing, setting the stage for decision. So today we'll delve into a crucial steps involved in hypothesis testing, a fundamental process in statistical inference. Will be look at how we set the criteria for making decisions about our hypothesis and how we compute the necessary test statistics. So, our first key step, as shown in this slide, is to set the criteria of our decision. This involves defining two important concepts. First one is the alpha level, or what we call the level of significance. And the second one is the critical region. So the alpha level is denoted by a sign, which means alpha, is the probability value that we use to define the unlikely sample outcomes if the null hypothesis were actually true. Think of it as a threshold rejecting the null hypothesis. Common alpha levels are 0.05, 0.01, and 0.001. For instance, if I set a alpha equals 0.05, it means we are willing to accept a 5% chance of incorrectly rejecting the null hypothesis. This is also known as a type 1 error. The critical region consists of the extreme sample values that are considered very unlikely to be obtained if the null hypothesis is true. The boundaries of this region are determined by our chosen alpha level. If our sample data falls with this critical region, we reject the null hypothesis. So visually, this region is often presented by the shaded tails or of a probability distribution. Slide please. So this slide provides a visual presentation of the critical region of a two-tailed test with an alpha level of 0.05. So we assume a normal distribution. In this sample, the total area in the critical region, so the shaded part tail is equal to our alpha level 5%. For a two-tailed test, this 5% is split equally into the both tails, meaning there's a 2.5% each tail. So like natunga sila. The boundaries of the critical region are determined by the z-scores that correspondent to these tails probabilities. In this case, for a alpha equals 0.05, and this in a two-tailed test, the critical z value are approximately around negative 1.96 and a positive 1.96. If our calculated test statistics falls below negative 1.96 above positive 1.96, we would reject the null hypothesis. So in this slide, we're going to tackle about the collect and compute. So once we establish our decision criteria from what we did earlier and what I've explained, the next step is to collect our data. We need to collect, and after that, we need to compute appropriate test statistics. This slide highlights the crucial stage. This is very important. So the test statistics is a value calculated from our sample data that allow us to assess how far our sample mean deviates from the population mean stated in the null hypothesis. This deviation is typically measured in terms of standard error. So as you can see, like naa siya ay formula. So na siya formula where as you can see z equals to m over the U. So this U represent the population mean over the standard error of the mean, where a larger z score, either a positive or negative, indicates a greater difference between our sample mean, and hypothesized population mean, making it more likely that we will reject the null hypothesis. So this slide provides a concrete examples of the calculating the z statistics. Let's say we have the sample mean is 95 and the hypothesized population is 85 and the standard error of the mean is 1.13. So plugging this value, the z statistics formula we get is z equals to 95 minus 85 over the standard error of the mean, which is the 1.13, is equals to 10. Kaya minus 1 ang 95 over 85, so 10 divided by 1.13 is equal to 8.85. So in this sample, we calculated that z statistics is 8.25. So we could compare this calculated z values to the critical z values. We determined in the step 2 example the like earlier the positive 1.96 for a 2-tailed test with a alpha equals 0.05. Since 8.85 is far beyond the critical value, we would likely reject the null hypothesis. So, and overall, setting the criteria of our decision by defining alpha level and a critical region and then computing the appropriate test statistics are very essential steps in hypothesis testing. These steps allow us to quantify the evidence against the null hypothesis and make an informed statistical decision based on our data. The example illustrated how the calculated test statistics against predefined critical region to determine whether it is going to reject or to fail to reject the null hypothesis. That would be all. Thank you.
So my name is Chester James Guliban, and I'll be discussing furthermore about hypnosis hypothesis testing. So risk in decision making and errors. Using hypothesis testing involves the risk of reaching an incorrect conclusion. You might wrongly reject a true null hypothesis, or conversely, you might wrongly not reject a false null hypothesis. These types of risk are called type 1 and type 2 errors. So type 1 error that occurs when the null hypothesis is rejected even though it is really true. So the researcher identifies a treatment effect that does not really exist, or a false positive. A common cause and biggest problem is sample data are misleading due to sampling error. A significant difference reported in literature even though it isn't real. Type 1 errors and alpha level equals probability of committing a type 1 error. So lower alphas equals less chances of type 1 error. So type 2 error. error that occurs when the null hypothesis is not rejected, even it is really false. The researcher does not identify a treatment effect that really exists, or a false negative. Common cause and biggest problem: sample mean in not in critical region, even though there is a treatment effect. Overlook effectiveness of interventions. Type 2 errors and probability. So beta equals probability of committing a type 2 error. So an example of this is this table right here. Truth in the population: there are true and false decision, retain the null and reject the null. So there's correct one to alpha, and type 1 error is just alpha, and the false side is we have type 2 error, which is beta, and the correct one is 1 to beta power to the power. Hypothesis testing two-tail example. So collect data and compute statistics intervention to 9 students. Mean exam score is M equals 90. So to provide this answer is we have to compute the given example here. We have a decision fail to reject H. So at the left side we have a reject H, which is a negative 1.96, and the right side we have reject H, which is positive 1.96, and at the middle we have Z equals 0, and we have 85 the below, and M equals 90.
This example demonstrates how to conduct a one-tailed hypothesis test using a sample data. So the population has a mean of 85 and a standard deviation of 8. The null hypothesis states that the sample mean is less than or equal to 85, while the alternative hypothesis claims that the sample mean is greater than 85. With a significance level set at 0.05, there is a 5% risk of rejecting the null hypothesis when it is actually true. In this case, an intervention was applied to 9 students, resulting in an average exam of 90. The standard error of the mean is calculated as 8 divided by the square root of 9, which is equals to 2.67. The z-score is then found by subtracting the population mean from the sample mean and dividing the standard error, resulting in a value of 1.87. For a one-tailed test at the 0.05 significance level, the critical z value is 1.65. Since the calculated z-score of 1.87 is greater than the critical value, the null hypothesis is rejected. This means there is enough evidence to conclude that the intervention increased the mean exam score above 85. The choice of alpha level is important, as it determines the cutoff for statistical significance and the probability of making a type 1 error, with the common values being 0.05, 0.01, and 0.001.
Let's talk about testing the null hypothesis and factors that influence our ability to detect a significant result. Now, let's look at the z-score formula. We calculate the z-score using this formula. Z equals the sample mean minus the population mean divided by the standard error of the mean. This tells us how far our sample mean is from the key population mean is standard error units. There are a few key factors that influence this calculation. The first factor is the magnitude of the difference between the sample mean and the population mean. The larger the difference, the bigger the numerator in our formula, and more likely we are to find a significant result. The second factor is the variability of the scores in the population. This affects the standard error, or sub m, which is the denominator of the formula. More variability means a larger standard error, which makes it harder to detect a significant difference. This slide shows a non-directional or two-tailed hypothesis test, where we're looking for differences in either direction. The shaded areas are both ends representing the critical regions, where if our z-score falls, we would reject the null hypothesis. The size of these regions depends on the significance level or alpha. For example, at significant level 0.05, the critical z values are positive or negative 1.96, and as the alpha gets smaller, the critical values moves further out, making it harder to reject the null.
Directional one-tailed hypothesis tests look for an effect in a specific direction, placing the rejection region in one tail of the distribution. Conversely, non-directional or two-tailed tests examine for an effect in their direction, splitting the rejection region across both tails. The decision is to reject the null hypothesis is influenced by the magnitude of the difference between sample and population means. The variability of the data as the sample size, larger difference, lower variability, and a larger sample increase the likelihood of rejecting the null hypothesis.
Alternative hypothesis. Using two-tailed tests for alternative hypothesis, it do not specify direction or difference, and do not hypothesize whether sample mean should be lower or higher than population mean. While using one-tailed test, it specifies a difference, and the hypothesis specifies whether sample mean should be lower or higher than population mean. Null hypothesis is using two-tailed test in null hypothesis, it specifies no difference between sample and population. When it's for one-tailed tests, it specifies the opposite of the alternative hypothesis. For example, null hypothesis. In null hypothesis, mu is lower than 85, so there is no increase in test scores. While the alternative hypothesis, if mu is greater than 85, there is an increase in test scores. The effect size. Problem with hypothesis testing. If significance is not equal to meaningful, important, or big effect, treatment effect compared to standard error. Significance is relative comparison and treatment effect compared to standard error. Effect size is the statistic that describe the magnitude of an effect. It measures size of treatment effect in terms of standard deviation in population. Cohen's d is not influenced by sample size. Cohen's d formula is mean difference over standard deviation. And while in evaluating Cohen's d, the d is equal to 0.2 or small effect, mean difference is equal to 0.2 standard deviation. While in medium effect, mean difference is equals to 0.5 standard deviation, and large effect is mean difference is equals to 0.8 standard deviation. It is calculated the same for one-tailed and two-tailed tests. Statistical power. Probability of correctly rejecting a false null hypothesis. The probability of correctly rejecting a null hypothesis is when it is not true. And when if one really exists, the probability that a hypothesis test will identify a treatment effect, priority, and calculate power before collecting data, sample size, expected effect size, significance level of hypothesis test, determine probability of finding treatment effect.